Hello, my name is I.Dranitskiy. I'm from CognitiveAgroPilot team, and I want to tell you about our product, AgroPilot. It is an autonomous control system for agriculture machinery, and mostly for the combine harvesters. Okay, so first of all, I want to tell you about the tasks of the combine harvester operator, which should be done simultaneously during harvesting. The first task is the controlling of the harvesting process. So the harvester operator should simultaneously control the parameters of the process, fine-tune some parameters, and so on. So the second point connected with the first one is the control of the vehicle speed to increase the efficiency of the harvesting. So the operator should check the current should check the parameters and tune the speed of the vehicle to increase the efficiency. The next task is the steering control along the path, crop edge, rows for corn or sunflowers, and so on. And another important case, of course, is the safety control of the obstacles in front of the vehicle and so on. So our product, CognitiveAgroPilot, automates the tasks connected with the vehicle motion. So it is the steering control, control of the vehicle speed, and safety functions, emergency stopping in front of the obstacles, or alarming to attend the operator of the harvester. So on this picture, you can see the harvesting of the wheat on the left side and harvesting of the corn rolls on the right side. In first case, the operator should minimize the cross-track error between the edge of the header and the edge of the standing crop. If the gap between these edges is too high, it is a problem because because of the lack of the efficiency. If otherwise, it is also the problem because it is a direct loss. So when we're talking about the harvesting of the corn rows or the corn or of the sunflowers, it is important to position the header, the teeth of the header between the corn rows. It should be done very precise, and the error about 15 centimeters is a problem. So our system could do it with very high accuracy all over the time. So now I want to tell how it could be done, what sensors and actuators we use in our system. So the main sensor of our system is an RGB camera for the tasks. When we use very wide headers, we can use 2 cameras, and all the algorithms are based on the computer vision. So we also have wheel angle sensor and receiving the speed of the vehicle from the CAN bus to calculate the odometry to get the information about the position of the vehicle between the camera frames. And also we have the inertial measurement unit to increase the accuracy of the positioning of the camera between the frames. So for actuation, for controlling the steering, we use the hydraulic control unit because the on on all the harvesters use the hydraulic steering, and for the speed control we use electromechanic speed control actuator. So here is the structure of our pipeline. It is a very it's traditional pipeline. So data from the sensors is an input for perception module, localization module, and the output from these modules forwarded to motion planning algorithms, which outputs the target control to actuators, steering or speed actuators. So now I want to tell a few words about the pipeline of perception for the case of crop edge detection when we're moving along the edge of the standing crop, for example, wheat. So the image from the camera forwarded to the neural network, which performs semantic segmentation. And on the left image, you can see the result of the semantic segmentation, where the every color connected means the appropriate class of the image. For example, gray is the standing crop, green is a field, and red is a machinery in front of the vehicle. So after that, the output of the segmentation neural network forwarded to post-processing algorithms, where we should perform the obstacle detection and also the target trajectory detection, so the crop edge detection. One more algorithm which is performed in parallel is crop height estimation. We need it to we need it because we detect the crop edge at the highest points of the edge, but we should control the vehicle in the ground plane. So we need to reproject our detection to the ground, and we need information about the height in this case. So, and we also have some algorithms of merging the detections between the frames to increase the accuracy and stability of the of our detection of the trajectory to control. So the same pipeline is done for the corn rows detection. On the left side, you can see the corn gaps between the corn in red. And on the right image, you can see the output from the post-processing algorithms. So it is a trajectories to control on the ground plane. So now a short video how our system works. You can see the operator uses our display to turn on the system, and after that the harvester autonomously guides along the crop edge, and you can see that the gap between the header edge and the crop edge is very small, and so the control is done with very high accuracy. So, and it works on different models of the harvesters. We can install our system on every model of the harvester on aftermarket, and so the operator have some time to use the phone. And on this video, you can see the harvesting of the corn in winter. So it's a strange case, but sometimes it could be done in during the winter time in Russia with snow. So and we had no problems with this. Everything was fine, and all our algorithms worked fine in this case as well. So now I want to tell a few words about the tasks that we also have done to make our prototype production ready, to work for seasons without any intervention from our side. And the first thing is a self-diagnostic system. For example, a usual case when when the dust appears on the lens of the camera, the accuracy of the control decreases, and operators can ask our help desk what is the problem. But we designed it to include the dusty lens detector in our system. So if the problem appears, the operator has the message, check the lens, and can solve this problem by himself. And the same thing is for sensor calibration tasks. We can understand what is the problem and show the message if the problem appears. And one more point that is very important is the telemetry data collection and remote control. So our AgroPilot units simultaneously sends us telemetry data during the harvesting, and also some images of the harvesting from time to time. And in case of some if some problem appears, for example, if the system was manually disengaged, we will receive the picture and could check what is the problem. So it is much easier to troubleshoot, to find some problems, to increase the quality of our product. And also, these images is very important to for learning our neural networks. So the more harvesters with our system is used, the more data we receive and the more powerful our neural networks becomes. So we are increasing the quality every time. So, and also we have a subsystem for the remote updates, so we can send the updates over there if we have a new version of neural network, if we have a new version of our system, of some subsystems, we can send it directly to the harvesters without the and we don't need to send the engineer to the field. Everything is done over the air. So that's all. Thank you.